Assalamu alaikum wa rahmatullahi wa barakatuh, and we are live for today's edition of the VOC Matric Revision 2022 session, and we are covering the subject of physical science, focusing on paper 2, organic chemistry and bonding with facilitator Muntasir Kadri from Intune Tutoring, and you can also follow this session on YouTube as well. That's the Voice of the Cape YouTube channel. And I'll hand over to you, Muntasir, to proceed.
Okay, Assalamu alaikum wa rahmatullahi wa barakatuh, everyone. So today we will be covering organic chemistry, bonding paper 2. Just give me 1 second. I just need to open my whiteboard. Okay. Okay. I don't know what's going on, so I need to
Okay.
repair that.
All right. As Muntasir is trying to sort out the slide on the other side, remember that the session is also recorded, so you can always refer back to the session. And please do share the link with anyone who can benefit from this session, especially those who matriculants who have taken up the subject of physical science and they can benefit from the lessons today. These are obviously questions that are covered in paper two. So, Muntasir, when you're ready, I'll hand over to you, inshallah.
Okay, we can continue. I'll just have to do it without the whiteboard for now. Just carry on.
Okay,
Okay.
all right.
So we'll be looking at paper 2, right? And this will be covering things like bonding. So this is where it's important to understand the differences between your intermolecular forces and intramolecular forces. Now, specifically when we're looking at bonding, things like boiling points and gases and vapor pressures and all those kinds of things, we are speaking about intermolecular forces, the forces that keep molecules together, or the forces that are interacting between various molecules. Okay, now to get a better understanding, I don't have my whiteboard, unfortunately, so I'll just have to do it like this. But what I'll do is I'll show you over here a few interesting things, which will be very helpful. So if we go here, here's the different type of bonds that they speak about, right? Physical properties and structures. So just to get an understanding, if we look over here, intermolecular forces are the forces that act between molecules, as we mentioned. And some of the forces that are important to understand are your dipole-dipole forces, your hydrogen bonds, right? And then there's also induced dipole forces. So if we look at dipole-dipole forces, this basically states when one dipole molecule comes into contact with another dipole molecule, the positive pole of the one molecule will be attracted to the negative pole of the other. So what is a dipole? If you think about the word dipole, this just means two poles, like the planet is a dipole, right? There's a north pole and a south pole. But in the case of atoms, when they're speaking about molecules and atoms and they speak about dipole, they're actually speaking about the fact that the one end of the molecule has a slight positive charge and the other end of the molecule has a slight negative charge. And this creates a dual polarity. And what happens is, as you know, opposites attract. And what happens is, within the same molecule itself, let's say it's a liquid of, let's say water, let's say the liquid's water, and water will have a partially negative charge on the oxygen atom because of its high electronegativity, and it will have a partially positive charge on the hydrogen atom because what's happening is the oxygen, due to its high electronegativity, it loves electrons, so it's pulling the electrons on the hydrogen towards it, making the hydrogen end partially positive. Now, of course, a special type of dipole-dipole would be hydrogen bonding, and we just spoke about water. So if we look over here, here's an example, and hydrogen bonding occurs between hydrogen and oxygen, hydrogen and nitrogen, hydrogen and fluorine. And all three of these atoms are highly electronegative, meaning they love electrons. And that's essentially what's happening here. The oxygen is negatively charged and the hydrogen's positively charged, and it creates a hydrogen bond amongst them. Now, amongst all intermolecular forces, your hydrogen bonds are essentially the strongest. That's why water has such a high boiling point, and some other gases vaporize rather easily. For example, like fuel. So if you go to the garage and you get that lovely smell of petrol, there's some people who really love that smell, and that is because those fuels like your octanes, they have a low boiling point, so they turn into gas easily, right? And that's the smell you're getting in the garage. Okay, it's because they evaporate rather easily. Now they don't have hydrogen bonds, they will then fall under things and things like this, and they'll have like what's called van der Waals forces. Now van der Waals forces consist of two types of bonds, right? Our induced dipole forces and our dipole induced dipole forces. Now don't be afraid by these terms. If you understand what a dipole is, as we just mentioned, two polar ends. Induced meaning it's inducing a dipole onto another one. It's causing another one to be polarized, right? So if we look at this, let's say a dipole-induced dipole intermolecular forces are also sometimes called London forces or dispersion forces. Right? So you would have heard these names before, right? London forces or dispersion forces. So London or dispersion are types of van der Waals forces. So they state here, and these are in nonpolar molecules specifically. So in nonpolar molecules, the electronic change is usually evenly distributed, but it is possible that at a particular moment in time, the electrons might not be evenly distributed. Yes. Now, this makes sense because electrons are constantly moving. They are never stationary. They're constantly revolving around the atoms in multiple directions. And we can never really pinpoint exactly where these electrons are at any one point in time. And that's why at some point in time, there may be a charge on the molecule, right? And in that moment where it's charged, it can induce a dipole, right? Because of the way the electrons are moving. But this dipole is, of course, temporary. It may not be permanent, and that's why it is weak. It's not a permanent one, unlike these hydrogen bonds over here. Okay. Then we have dipole-induced dipole forces. These forces exist between dipoles and nonpolar molecules. The dipole induces a dipole in the nonpolar molecule, leading to a weak, short-lived force which holds the compound together. So what I want you to keep in mind is hydrogen bonds, strong. Okay, so remember, dipole-dipole forces are the strong intermolecular forces, and your van der Waals forces, like induced dipole and dipole-induced dipole forces, are your weak forces. Now, let's quickly jump back to the question paper. Just wanted to get those definitions out of the way so you have a better understanding, because those are what usually confuse the students. Now, if we look here, learners use compounds A, B, and C to investigate one of the factors that influence the vapor pressure of organic compounds. We have butane 1-ol, butane 2-one, and propanoic acid. So if we look at these molecules, butane 1-ol is an alcohol. What does that tell us? At the end of the molecule, there's a hydroxyl group. So we have oxygen and hydrogen. Remember, we spoke about hydrogen bonding, right? If we have hydrogen and oxygen, we can assume that we can easily assume that within the molecule, we are going to have hydrogen bonds as well. We have butane 2-one, which is a ketone. Okay, if you remember the structure of a ketone, I'll just show you over here quickly. Structure of a ketone, sorry, spelled it incorrectly. So if you quickly look at the structure of a ketone, and I'll zoom in on it for you. So it has a double bonded oxygen over here. Let me just make it bigger. There's a double bond oxygen over here, and then there's an oxygen over here with a, and these R's just represent a random carbon change that may be on either side of the molecule. So once again, we have some sort of polarity on the oxygen. So it is possible to also get a dipole-dipole force on this molecule. Now, if we go back here and we look at propanoic acid, well, this is a carboxylic acid. This has C double OH. That's how you know when something's in a carboxylic acid. It has C double bond O and a dash and a OH. Now, if we look here, they say define the term vapor pressure. Okay, so let's just look at the quick definition for it. It says here, this is how they would mark you. So you get 2 marks for this definition. The pressure exerted by a vapor at equilibrium with its liquid in a closed system. So if you wanted to measure the vapor pressure, let's say, for example, of gasoline, right? You have it in a container. The container would be sealed tightly. It would be unexposed to the environment. And a vapor pressure would build up in that container, and that can be measured. And that would be the vapor pressure of that specific vapor. Specific liquid, right? So every molecule that would turn into a vapor at some point would have its own vapor pressure. Now, write down the independent variable for this investigation. So, of course, if we look at this investigation, we are trying to find out what the vapor pressure of each of these molecules are. So, therefore, vapor pressure is the dependent variable. So, what does the vapor pressure therefore depend on? Well, it depends on the type of molecule. And within each molecule, they have their own different types of bonds. So, therefore, the independent variable would be the intermolecular forces. Let's ask in 3.3, which compound A or B has the higher vapor pressure? So this is, of course, a tricky question because here we've got butanol and propanoic acid. Now if we go here to here, they'll tell us that B would be the answer. Now, why would they state B? Okay. Well, if we look here, butan 2-one and butan 1-ol, if I could draw, well, I can't really draw you the structure now, but this has an OH group at the end, and butan 1-one, if we look at ketones like we did over here, we can see the C double bond O over here and this OR over here. So it has these two highly electronegative oxygens. So it may have a partially negative charge here and a partially negative charge here. So this molecule is quite polarized. Right? And because it's a polar molecule, which is important, it will have the stronger bond. So this molecule would then bond, for example, with one of the hydrogens on the same ketone, and that would create what we know as dipole-dipole forces or hydrogen bonds. Right? Or it could be one of the special hydrogen bonds where the oxygen bonds to the hydrogen. Right? So let's go to the next question, 3.4. Okay, fully explain the answer to question 3.3. Include the types of intermolecular forces in your explanation. So let's look at what they say. So if we look here, compound A, butan 1-ol, has hydrogen bonding, dipole-dipole forces. Okay, compound B, butan 2-one, has dipole-dipole forces and London forces between the molecules. Right, so it has both, and that makes sense because the ketone itself would have a carbon chain on either side of the molecule, and that's where our London forces would exist. And our dipole-dipole forces are because of the oxygens that we have, possibly bonding also to hydrogens, creating dipole-dipole forces. Right? And then they state here, intermolecular forces in compound A, butan 1-ol, are stronger than intermolecular forces in compound B, butan 2-one. This is correct. Hydrogen bonds are a lot stronger than simple dipole-dipole forces. Okay. If we carry on, they state here, more energy is needed to overcome or break intermolecular forces in compound A. Now, if you think about water has hydrogen bonds. Water boils at 100 degrees Celsius. So that means you require a lot of energy to break the bonds within water to even cause it to become a gas and evaporate. They state here, okay, it's the same thing. And yeah, that's it. So more energy required so this obviously the stronger the bond, remember, more energy is going to be required to break that specific bond. Therefore, the temperature required is also going to be higher. Now, let us look at 3.5. Okay, so in this example, the graph below represents the relationship between vapor pressure and temperature for compound A. Okay. Now, something important to note: your vapor pressure is dependent on the bonds between your molecules. Now, this this concept is kind of counterintuitive. So you have to think of it this way. Okay. If your molecule has weak intermolecular bonds, Okay, that means it's going to be easier to break those bonds. If it's easier to break those bonds, it's easier for that molecule to become a vapor. If something turns into a vapor quite easily, it means more vapor will exist than there is liquid, and therefore the vapor pressure would be greater in something where the bonds break easier because you are creating more vapor. So that makes sense, right? Of course, if something has a stronger bond, the vapor pressure would be a lot less because it's harder to turn it into a vapor. Now, let's say here, okay, let's look at it again. The graph below represents the relationship between vapor pressure and temperature. For compound A at sea level, X and Y represent different temperatures. So here they're giving us the vapor pressure. Here they're giving us the standard vapor pressure of 101.3 kilopascals. Remember when you speak about standard temperature pressure, this is one of the things that's a standard pressure, 101.3 kilopascals. Right? You know your standard temperature is 25 degrees Celsius. Now, if we look at this, right, they ask us write down the term for the temperature represented by X. And what do you think that would be? Well, if we look at the image, here's our vapor pressure slowly increasing, slowly increasing. We reach standard pressure, and now we all of a sudden peak past it. So that means at this point, right, this specific compound, compound A, which is butane 1-ol, is actually being vaporized. It's reached boiling point, and now the vapor pressure is increasing exponentially. Right? So this would be your boiling point. In 3.5.2, state the phase of compound A at temperature Y. Choose from gas, liquid, or solid. Of course, this is going to be gas. If something's peaking past boiling point, it's going to be a gas. So therefore, this is what we're looking at. 3.5.3. Redraw the graph above in your answer book on the same set of axes. Sketch the curve that will be obtained for compound C. Clearly label curve A and curve C. Now, what we do is we look at the molecules. And we see that butane 1-ol will have hydrogen bonds. They're going to be quite strong, very difficult to break. But propanoic acid is going to have, in this case, propanoic acid should have the weaker bond, but let's just double check. If we go down here, below the curve, compound C. Oh, sorry, actually, propanoic acid actually has the stronger bonds because of the two oxygens, right? So there's a greater chance that the bonds are going to be stronger because those oxygens are creating dipoles within the acid itself, right? So it's going to be harder to evaporate the propanoic acid as opposed to the butane 1-ol. Okay, and then what we get on this image, if we go down here, and I'll just zoom in on the graph a bit for you, we see that compound C, okay, is down here in terms of vapor pressure, and compound A is up here. So this means that compound A is evaporating easier. The bonds are being broken easier, even though they are hydrogen bonds. But these dipole-dipole forces over here of the ketone are much stronger than that of the alcohol. And therefore, as the temperature increases, this does not evaporate as quickly. And its boiling point is actually, the temperature at which it boils is going to be higher, and therefore the vapor pressure is going to be smaller than that of compound A. Right. Now, let's go down. Okay, example 2. The relationship between boiling point and the number of carbon atoms in straight chain molecules of aldehydes, alkanes, and primary alcohols. Okay, so now we need to try and understand what these functional groups are. What are they? Okay, so this is where understanding your functional groups come in. So let's look at quickly what an aldehyde is. And if you look at an aldehyde, this is it. So we have an odd group here, a hydrogen here, and a double bond O over here. So this is an aldehyde. right? And we can see there's an oxygen, there's a hydrogen. So once again, in this molecule, we can have a partially negative here and a partially positive over here. So keep that in mind for the functional group. Here's a potential for dipole forces. Remember, when you see oxygen, immediately you must think dipole. That's what's going to happen. It's always going to be dipole. Then the next one is alkanes. Alkanes are very simple. We all know what alkanes are, right? Those, and for those who don't, I'll just pull it up as well. If we go here and we look at some alkanes, and if we look at the functional group, an alkane is just a carbon chain with single bonds strictly. Remember, alkanes are single bonds. Alkenes, there'll be a double bond within the chain. Alkynes, there'll be a triple bond within the chain. Now, there'll be no other elements attached to this alkane, unless maybe they decide to add something electronegative like bromine. Then we can get a bromoalkane, like we can get bromomethane, bromoethane, all those kinds of things, and that could shift could cause a shift in polarity on the molecule. But if there's no electronegative atom attached to it, what we have then are weak van der Waals forces. And notice methane, which is a gas, right? Ethane and propane. We all know propane as well, right? That's often butane and propane are often used as lighter fluids, right? And you'll notice in the lighter there'll be a liquid, right, which is butane. And the moment you press on the a little button on the side without clicking the flint, you press on the button on the side, you'll hear the gas coming out. That's because there's a buildup of vapor pressure with inside there. Now, of course, maybe you're wondering, now why doesn't all the liquid turn into vapor? Well, it can't. What happens is the vapor pressure builds up. There's a maximum amount of gas that's sitting in the lighter, and the rest at the bottom cannot evaporate. And there's a kind of equilibrium within the lighter itself, and pressure builds up. And when you press the button down, the pressure is released and the gas comes out. Okay, and that just goes to show that these bonds are very weak, and you can just strike a flint and there we go, it lights on. So it's quite volatile because its bonds are so easily broken. So those are alkanes. So now we can understand, oh, alkanes, no electronegative atoms, no oxygens, no bromines. Remember, everything on the right side of your periodic table, okay, if you're looking at your group 6, 7, group 6 and 7, yes, group 6 and 7 on the periodic table, those elements are highly electronegative. And if any of them exist on an alkane, they can adjust the polarity, right? Now, that's not in this case. This is just a simple alkane. And then we have primary alcohols. And what does this mean? Well, this has got to do with the position of the alcohol. And a primary alcohol is where the alcohol is attached to the first carbon on the molecule. Remember? So first carbon would make it a primary alcohol, second carbon, secondary alcohol, and your third carbon, a tertiary alcohol. Now, they go on to tell us curves, they say the relationship between boiling point and the number of carbon atoms in a straight chain molecules of aldehydes, alkanes, and primary alcohols is investigated. Curves A, B, and C are obtained. Define the term boiling point. And this is where you're going to speak about atmospheric pressure and vapor pressure as well. Right? So if we look at this over here, the definition that they give us, we'll scroll down. The temperature at which vapor pressure equals atmospheric pressure. So now there's a really nice equation that you may know, which is PV equals nRT. Pressure times volume equals number of moles times Reynolds constant times temperature. Okay, now that equation itself kind of explains this definition over here, where the temperature at which vapor pressure equals atmospheric pressure. So if our vapor pressure is equal to our atmospheric pressure for a specific molecule, then we've reached boiling point, right? Now, write down the structural formula of the functional group of aldehyde. So we did look at it, and here it is over here. There's the carbon. Here's some random odd group over here, double bonded oxygen and a hydrogen. The graph shows that the boiling points increase as the number of carbon atoms increase. Fully explain this trend. So if you look at this, All right, here we go. So C is okay. So here's the number of carbons on our x-axis. Here's our boiling point on our y-axis, and here they're showing us that as the number of carbon increases, so does the boiling point. And this is for multiple reasons. Number one, the mass is increased. So the more you have, the more energy you're going to need to break up the molecule. Okay, so of course, mass plays a role there in the increase in temperature. We can look at the memo and see what else it says. So your increasing number of carbon atoms. So your state increases molecular mass, size, chain length, and surface area. The other one is the strength of the intermolecular forces. If there are more sites, for London forces, it's going to be harder to break up the bond. Okay, so of course, if you, let's say, have two oxygens, or you have quite a few electronegative atoms sitting on the chain, then that's going to make it very difficult to break up, and that's going to increase our uh, temperature at which it's going to boil. More energy is needed to overcome or break intermolecular forces, and that is also true. Right? And those are basically the three reasons. So you can easily just say there's an increase in molecular mass size or chain size. Okay, the strength of the intermolecular forces determines the increase in boiling point, and as a result, you will need more energy to overcome or break said intermolecular forces. Now, let's see. What's the next question? Identify the curve A, B, or C that represents the following compounds with London forces only. So, which one is going to have the London forces? Well, of course, those with the highest boiling points. And I would say, well, it could either be A or B, right? In this case, I mean, they're not asking us for two options. It is kind of a tricky question, but in this case, I would simply say A straight off the bat because it's got the highest boiling point. Okay, and if we go down, wait, London forces only, C boiling point. This is a bit odd. It should be A because the boiling point is high. Why are they saying C? Compounds with London forces only. Yeah, Oh, my apologies. I made a mistake. Sorry. I got confused between dipole, and London. So these London forces are van der Waals forces. They're weak bonds. So just C is the correct answer, right? So remember, London forces and van der Waals forces are the same thing. So you get London dispersion forces are a type of force that exists within van der Waals forces. Okay, and those are one of the weakest forces. The bonds aren't very strong. The aldehydes, explain your answer. So remember, we saw the aldehyde, right? It had a double bonded oxygen to it. So if we take a look here, this would most likely be B, right? Because A would have your hydrogen bonds because it's OH, it's straight to the bat and OH. Okay, so here we're going to be, okay, aldehyde is going to be B. Explain your answer. So once again, it comes down to the type of intermolecular forces. Compare strength of intermolecular forces of A, B, and C. Compare boiling points or energy required to overcome intermolecular forces of alcohols A and aldehydes B. So of course, the amount of energy required to overcome intermolecular forces of alcohols is greater than that of aldehydes. Alcohols have the highest boiling point. And why is this? Well, they have the hydroxyl group at the end of the organic compound. And so that means it's easier for them to form hydrogen bonds, which are not a van der Waals force, but rather a dipole-dipole force. Okay, and the other state, alkanes have the lowest boiling point, as we mentioned. Now, as we go further down, the state here, use the information in the graph and write down the IUPAC name of the compound with a boiling point of 373 Kelvin. Now, that would be this compound over here, which is an alcohol. And the IUPAC name for this alcohol, well, this is an odd question. They're not giving many clues. Do they tell me how many carbons? Use information in the graph and that the IUPAC name of the compound with a boiling point of 373 Kelvin. Well, if we think about 373 Kelvin, And let's see what that is in degrees centigrade. Where's my calculator? So 2, well, this is simple. So remember 3, 1 Kelvin is equal to negative 273. So we just go 373 minus 273. That's going to give us a value of 100 degrees centigrade. Okay. So what boils at 100 degrees centigrade? Well, water for one. So let's see if we are correct. Yeah, we scroll down. We go. So in this one, that's no. Where is this answer now? Question 3.5. Let me just zoom out so I can see. There we go. So 3.5. So in this case, it may not be water, but butanol is the answer. Did they give us any examples here? No, they didn't. So this is just some general knowledge that you should know. You are supposed to know that butanol boils at 373 degrees Kelvin. Right? Let's carry on and let's go down to write down the IUPAC name of the compound containing 5 carbon atoms, which has the lowest vapor pressure at a given temperature. So 5 carbon atoms, lowest vapor pressure. So it's not a high vapor pressure. So don't mix it up, right? So a low vapor pressure means that it's not evaporating easily. So it must have a strong bond. Okay. So therefore, this is most likely a type of alcohol. So we've got Michael eats peanut butter. That's 4 carbons, still butane. And then when we get to the 5th carbon, now we just say pent, right? So for 5 carbons, we're going to go pent. We got pentane, but if it's an alcohol, it should be pentanol. And let's see if we are correct. And there we go. Pentanol. Specifically pentan 1-ol. And the reason they say 1-ol is because at the end of the atom, right? Of course, it's going to be easier to create hydrogen bonds if the alcohol is existing on the 1st carbon. There'll be no steric strain, there'll be no restrictions, there'll be no electrons floating around, restricting the intermolecular forces from forming. Right? So these two questions are actually rather tricky. You need to have a good understanding of how the molecules work and how they interact. And so when it comes to bonding, you actually need to just like do a little bit of intensive reading. But once you understand these concepts, they make the world of sense. Okay, so it's as simple as this. You just got to remember, for this section, the most important thing would be to understand these pieces of information here. So if we go down, once again, I'll zoom in. The most important things to understand is that you have dipole-dipole forces, and they consist of hydrogen bonds. What are dipole-dipole forces? Well, a dipole just means dual polarity. So for example, in this alcohol over here, which is ethanol, we have, guess what? A negative polarity over here and a positive one over here on the hydrogen on this hydroxyl group over here. And we have another alcohol over here, and we can see that the hydrogen bond is forming between these two. And if you look at where this alcohol is situated, on the 1st carbon, so it's a primary alcohol, and that makes it easy for it to connect and make this bond. And essentially, in the liquid of ethanol, you can imagine that if you could zoom in with a super powerful microscope and zoom in on the ethanol itself, you'd be able to maybe see all these molecules floating around each other, and these bonds forming amongst themselves. And that's how it stays in its liquid form. And once we break these bonds, guess what? The molecules separate, and now they start to evaporate. That's the picture you need to get. And then, of course, van der Waals forces. We have induced dipole. Remember that? That's where we're inducing a dipole upon another molecule. And that usually occurs because the electrons are constantly moving around the atoms. And as they're doing that, we may temporarily induce a dipole on a specific molecule, and we could then form a temporary bond, right, due to van der Waals forces. And now this specific one would be an induced dipole force. And then we have remember, a dipole induced dipole. These forces exist between dipoles and non-polar molecules. Okay, so what's happening is there's a dipole, maybe on one of the molecules. This molecule then comes into contact with the non-polar section of the same molecule and induces a dipole on that molecule, and that's why it's called a dipole-induced dipole force. And then that creates a very short-lived temporary bond on the non-polar molecule. And you may see these on alkanes, for example, right? That would be one of the most common ones you'd see them on. I'd say, yeah, that's about it. So just get your head around these definitions. And I know it can be troublesome, but if you just try to look at the molecules and understand what they're trying to tell you in relation to the definitions, I promise you, they will make the world of sense to you. If you do need these question papers and the answers, they are available on the Intune Tutoring website. Here is the webpage over here, www.intunetutoring.co.za. And if you would like further help from the institution, you can contact on this number over here. Okay, thank you so much for your patience and joining on this lesson. And I hope you enjoy the rest of the day. Assalamu alaikum rahmatullahi wa barakatuh.
Walaikum salam wa rahmatullahi wa barakatuh. Shukran very much for a very informative lesson today. We look forward to having you back tomorrow when we will be going through the session on mathematics, inshallah. So, shukran once again, and a reminder that the session is recorded. You can always refer back to it on the Facebook page as well as the Voice of the Cape YouTube channel. From myself, Konita Kamar, and my guest, Muntasir Kadri, we bid you farewell. Assalamu alaikum wa rahmatullahi wa barakatuh.